Welcome back to the Deep Dive. Today we're plunging into, well, what many consider the true workhorses of machine learning. Those incredibly versatile algorithms that seem to pull off magic sometimes. We're going to pull back the curtain on how they learn and, crucially, how combining simple models or even building these fascinating brain-inspired structures can tackle problems that a single standalone model just can't.
That's absolutely right. Our mission for this deep dive is to truly unpack the power of collaboration in machine learning. We'll explore ensemble learning, a paradigm where a group of models works together, proving that collective intelligence can far outstrip individual brilliance.
Okay.
We'll specifically delve into techniques like bagging, random forests, and then shift our focus a bit to the sequential improvement you see in the boosting family. So things like AdaBoost, gradient boosting, and the industry powerhouse, XGBoost.
And as if that wasn't enough to get your gears turning, we're also going to take a fascinating journey into the world of neural networks. Specifically, we'll be looking at multi-layer perceptrons. It's a full plate, definitely designed to give you that aha moment and hopefully equip you with a deeper understanding of these pretty sophisticated tools.
And to ground our discussion, make it less abstract, we'll see these techniques in action on two classic real-world data sets. They represent very different machine learning challenges.
Right. Which ones are you using?
First up, we have the MNIST handwritten digit recognition task. This is a multi-class classification problem, essentially, teaching a computer to reliably identify handwritten digits, 0 through 9.
The classic zip code reader problem, basically.
Pretty much. Each image is a small 28 by 28 grayscale pixel grid. When you flatten that out, it gives us 784 individual features. And we're working with a substantial amount of data here, a whopping 60,000 training examples and another 10,000 for testing. So it really ensures our models have plenty to learn from and then, prove themselves against unseen data.
Okay, so that's classification. What's the other one?
Then, for a completely different flavor of problem, we'll turn our attention to the California housing data set. This is a regression problem.
So predicting a number, not a category.
Exactly. We're not trying to categorize something, but rather predict a continuous value. In this case, we're trying to estimate house prices based on various attributes like their location, age, number of rooms, that sort of thing.
Gotcha. So that gives a good contrast.
It's an excellent way to see how these advanced algorithms handle the nuances of predicting real-world values versus just discrete categories. Understanding these two very different scenarios. One, a high-dimensional image classification task. The other, a more traditional tabular regression problem, will really highlight the unique strengths and sometimes weaknesses of each approach.
And that helps you, the listener, understand when and why to reach for a particular tool in your own machine learning arsenal. And truly, that's what this deep dive is all about. Not just knowing what these models are, but when and why they shine or, sometimes struggle. So, okay, let's begin our journey. Let's look at the very heart of collaborative intelligence. Ensemble learning, starting with, I guess, its foundational building block.
Sounds good.
So we begin with ensemble learning. As the name suggests, it's all about the power of collaborative intelligence. But before we get to the groups, we need to understand the individual players.
Absolutely.
Right? And our starting point for many of these ensemble methods is a surprisingly simple yet foundational machine learning model, the decision tree.
Decision trees are, they're remarkably intuitive. They kind of mimic how we humans often make decisions. And they're used for both classification, like identifying that digit, and regression, like predicting a house price.
How do they actually work?
Think of them as a series of simple cascading questions that lead you down a path to a decision. They operate by recursively splitting data based on feature values, basically, creating a flowchart. For instance, a question could be, is this pixel dark? Or, is the house older than 20 years? Each answer guides you to the next question until you eventually reach a final prediction, a leaf node in the tree.
And on paper, for the data they train on, they can be incredibly effective, often achieving seemingly perfect scores. But here's the crucial pitfall, the big challenge that makes them tricky for real-world deployment. Single decision trees have this notorious tendency to overfit the training data.
Right. That's the key issue.
So what does that mean for you, the listener? It means they learn the training data almost too well. They end up memorizing not just the underlying patterns, but also the noise, the outliers, the idiosyncrasies unique to that specific data set.
Exactly.
They perform fantastically, often flawlessly on the data they've seen.
Right.
but then they get tripped up, sometimes drastically, performing poorly on new, unseen data. It's like a student who memorizes every single answer for a practice exam, but then completely falters when faced with slightly different questions on the real test.
That's a perfect analogy. And to illustrate this overfitting phenomenon, let's look back at our MNIST digit recognition problem. A baseline decision tree classifier, when trained on its own, achieved an F1 macro score of 0.86 on the training set.
Okay, 0.86. How good is that?
Well, the standard deviation was very small, just 0.005. And for those less familiar, the F1 macro score is a really crucial metric for multi-class problems like this. It's essentially a balanced average of precision and recall for each class and then averaged again.
So it checks if it's good across all the digits.
Exactly. A high F1 macro tells us the model isn't just good overall, but it's doing consistently well across all 10 digits 0 to 9 without favoring one over another. That's vital for real-world applications, like you mentioned, automated postal sorting.
Okay, so 0.86 sounds pretty decent then for training.
It does sound pretty good, right? But then on the test set, the accuracy dropped to 0.88 or 88%.
Okay. Still decent, but not amazing.
Right. While 88% is a respectable baseline, it clearly leaves a lot of room for improvement. And it shows the model didn't generalize perfectly to unseen data, hinting strongly at that overfitting tendency.
And it gets even more dramatic when we look at the regression problem, the California housing data set, right?
Oh, absolutely. A decision regressor made 0 error on the training set.
0. Serious.
0. Perfect score, suggesting it completely nailed every house price in its training data. But then, when faced with new unseen housing data in the test set, it showed a really high error of $47.18 thousand with a standard deviation of $1.33 thousand.
Wow. So it went from perfect to, well, pretty bad.
This is a stark, almost textbook example of overfitting. The model essentially just memorized the training set, rendering it pretty ineffective for actual real-world predictions. It just couldn't adapt to the subtle variations or new patterns in the unseen data.
So what does this all mean for you listening? Overfitting is a critical problem because the ultimate goal of machine learning isn't just to understand the data you have. It's to generalize well to data it hasn't seen yet.
That's where the real value lies.
Exactly. And that's precisely why we need more sophisticated techniques. Techniques that can overcome this fundamental challenge and deliver truly robust performance.
Which brings us nicely to our first major ensemble technique, bagging.
Bagging. Short for bootstrap aggregating, right?
That's the one. It's specifically designed to reduce that variance and combat the nasty overfitting problem we just discussed. It offers a powerful remedy where those individual models fall short.
Okay, so how does it work? What's the core idea?
The core concept of bagging is, well, it's quite elegant in its simplicity, yet it's profoundly effective. Instead of training one single model, like our initial decision tree, bagging trains multiple independent base estimators.
Usually more decision trees.
Typically, yes. Decision trees, which, as we know, can be prone to overfitting on their own. But here's the trick, the secret sauce. Each of these multiple trees is trained on a different bootstrap sample of the training data.
Okay, unpack bootstrap sample for us. I know it involves replacement.
Right. So it's created by sampling with replacement from the original data set. Imagine you have a bag of, say, 100 uniquely colored marbles. You pick one, note its color, and crucially, you put it back in the bag. Then you pick again. You repeat this process 100 times. You end up with a new bag of 100 marbles, but because you put them back each time, some colors might appear multiple times, and some original colors might not appear at all in that particular sample.
So each tree sees a slightly different version of the data.
Exactly. This randomness in sampling, allowing for duplicates and omissions, is absolutely key. It makes each individual tree in the ensemble slightly different from the others.
Okay, so you train all these slightly different trees. Then what?
Then each individual estimator, each tree, makes its own prediction based on its unique slice of the data. And these predictions are aggregated.
Ow. Averaging. Voting.
Depends on the task. For regression problems, like predicting house prices, we might simply average their predictions. For classification problems, like digit recognition, we typically take a majority vote.
Like a committee decision.
Precisely. This aggregation process, pooling the opinions of many diverse models, produces a final prediction that's much more robust and less biased. Bagging isn't just a statistical trick. It's really a profound demonstration of the wisdom of crowds principle in machine learning.
Interesting.
Each individual tree might be biased or quirky, but by averaging their predictions, those individual biases tend to cancel each other out. Think about how multiple, slightly imperfect weather forecasts can yield a surprisingly accurate collective prediction.
Yeah, okay, I get that.
It's the ultimate strength in numbers play. It reduces model variance and helps ensure you get a robust, reliable prediction, not just one that looks good on the training data.
So when you're actually using bagging estimators, like bagging classifier or bagging regressor in, say, scikit-learn, what are the key knobs to turn, the parameters?
Good question. There are a few key ones. The base estimator is, of course, the underlying learning algorithm by default. It's usually a decision tree classifier for classification and a decision tree regressor for regression.
Makes sense.
Then there's nestimators. This isn't just a count. It's a lever for model complexity and performance. It tells the algorithm how many of these base estimators, these trees, to build.
How many is usually good?
Well, too few, and you might not fully leverage that wisdom of crowds effect. Too many, and you're just adding computational cost without significant gains. Finding the sweet spot often involves experimenting, finding a point where adding more trees doesn't significantly reduce errors or improve stability. It's a key dial for tuning your ensemble's overall power. Default is often 10, but you might need more.
Okay, what else?
You can also control the sampling process itself with max samples. This specifies how many samples to draw for each base estimator. It can be an integer for a fixed count or a float for a proportion of the dataset. Like max samples 0.7 means each tree trains on 70% of your training data, randomly sampled.
Right.
Similarly, max features dictates the number of features to draw for each estimator again, as an integer or a float. This introduces another layer of randomness, having trees specialize on different subsets of input variables, though this is more central to random forests, which we'll get to.
Got it. And the bootstrapping itself.
Right. The bootstrap parameter, which defaults to true, explicitly turns on sampling with replacement. That's the core of bootstrap sampling we talked about, enabling that diversity. And bootstrap features, defaulting to false, lets you decide if features are also drawn with replacement.
Okay. And there was something about out of bag.
Ah, yes, oops score. When you set this to true, and bootstrap must also be true, it allows you to use out-of-bag samples for estimating the generalization error.
What are out of bag samples?
They're the samples that weren't included in a particular tree's bootstrap sample. Because of the sampling with replacement, each tree only sees about 2/3 of the data on average. The remaining third is out of bag for that tree.
Oh, yeah.
These act as an internal validation set. It's a neat way to get an idea of how well the model performs on unseen data without needing to explicitly split off a separate validation set from your precious training data.
That is handy. Okay, so let's talk performance. Did bagging actually fix the overfitting problem?
Let's look at the numbers. For our MNIST classification task, remember that single decision tree got an F1 macro score of 0.86 on the training set.
Yep.
The bagging classifier dramatically increased that to 0.937 on the training set with a small standard deviation. That's about a 7 percentage point increase just during training, indicating it's learning a much more robust pattern.
Okay, better training score. But the real test is the test set.
Exactly. And this is where the real magic happens. On the test set, where the single decision tree gave us 88% accuracy, bagging jumped that up to a very respectable 94%.
Wow, okay, a 6% point jump? That's significant.
It really is. On a data set like MNIST, that difference isn't just statistical fluff. It could mean significantly fewer errors in, say, automated postal sorting, or a dramatic increase in reliability for a digit-based input system on a tablet or smartphone. It highlights how even seemingly modest percentage gains can translate into massive real-world impact. It really underscores the value of these ensemble methods.
Yeah, what about the housing prices? The regression task?
Good question. Remember the decision tree regressor had that high test error of $47.18 thousand?
Yeah, the one that got zero error on training.
Right. The bagging regressor reduced that significantly down to $35.35 thousand on the test set. The training error was around $14.41 thousand.
So a big improvement on the test error, and the training error isn't zero anymore, which suggests it's generalizing better.
Precisely. This clearly shows bagging's power in reducing errors on unseen data for continuous prediction tasks as well. We're seeing a substantial improvement just by moving from a single, likely overfit model to an ensemble that leverages collective intelligence.
It really works. Bagging effectively addresses that overfitting problem by reducing the variance of the base learners. Like you said, each individual tree might be a bit quirky or overfit on its own little sample.
Mm-hmm.
But when you average out the quirks of many different trees, trained on slightly different data subsets, those individual biases tend to cancel each other out.
Exactly. It leads to much better generalization on unseen data. It's truly a testament to the idea that there's strength in numbers, especially when those numbers are diverse.
Okay, so if bagging showed us the immense power of averaging out individual quirks by sampling the data, what if we could make those individual experts, those trees, even more diverse? What if we added another layer of intelligent randomness?
Ah, now you're thinking like the creators of random forest. That's precisely where the concept of random forest comes in. It's a truly supercharged evolution of bagging.
Supercharged how?
That's right. Random forest takes all the benefits of bagging the bootstrap sampling of data, training multiple trees, aggregating their predictions, and adds a critical innovation that further decorrelates the trees.
Decorrelates, makes them
Yeah.
less similar.
Exactly. In addition to bootstrapping the data samples, when a tree in a random forest is deciding how to split a node, it doesn't consider all the available features. Instead, it only looks at a random subset of features before deciding on the best split.
Okay, wait, so at each decision point in the tree, it only gets to choose from a random handful of the features.
Precisely. This subset size is typically specified by a parameter, usually called max features.
Huh. Why does that matter? Why add more randomness?
This additional layer of randomness is crucial. It further decorrelates the individual trees in the forest. Imagine if your top 3 most important features were always the same for every tree. Then every tree would likely split on those same features early on, making them structurally very similar, maybe even leading to similar errors.
Okay. They all rely on the same strong signals.
Right. By forcing them to consider different random subsets of features at each split, it makes each tree even more diverse and less prone to being overly influenced by just a few dominant features. This diversity makes the overall ensemble even more robust, further reducing the overall variance and leading to even better generalization. It's a brilliant way to ensure no single tree gets too comfortable or too specific in its view of the data.
Okay, that makes sense. So for the parameters in random forest classifier or random forest regressor, it sounds like they have the bagging stuff plus this new max features.
Pretty much. You'll find they include all the bagging parameters we discussed, like nestimators, bootstrap, OOP score, max samples, and random state. One thing to note is that for a random forest, the default nestimators is often higher now, maybe 100, not 10, like the basic bagging default. It reflects the general finding that more trees are usually better for random forests, up to a point, of course.
All right. More trees, more randomness, better result usually.
And because random forests are built from decision trees, they also inherit many of the decision tree specific parameters that let you fine-tune the individual tree's growth.
Like what?
Things like criterion, which measures the quality of a split. For classification, Gini's impurity or entropy are common choices. For regression, squared error is the default. You can also control the tree's maximum depth with max depth, or leave it as none to let them grow fully. Or min sample split, which sets the minimum number of samples required to even consider splitting an internal node.
So you can control how bushy or deep the individual trees get.
Exactly. Parameters like min impurity decrease or CT-alpha for pruning also give you that fine-grained control over how individual trees are constructed. This impacts their complexity and their own potential for overfitting, even within the forest.
But the really unique one, the defining parameter for random forest, is max features.
Absolutely. That's the one that sets random forest apart. It controls the randomness of which features are considered at each split. You can set it to auto or squirt, which usually means it will use the square root of the total number of features, or log 2 for the base 2 logarithm of the
So
features.
just a specific number.
Yep, you can specify an integer for a fixed number of features, or a float for a proportion, like 0.5 for half the features, or even none to use all features, which would essentially make it more like bagging in that regard. This specific parameter is what drives that additional decorrelation of trees, making random forest incredibly powerful.
Okay, let's get to the results. This is where random forest really shines, right?
It really does. On our Amendness classification task, remember, bagging got us to 94% accuracy. The random forest classifier pushed that even further. On the training set, it achieved an F1 macro score very close to 0.997, almost perfect learning on the training data.
Wow. Okay, but again, the test set.
And on the test set, it yielded an impressive accuracy of 0.97 or 97%.
97%, that's another big jump.
It's a 3 to 4 percentage point improvement over bagging, which was already good. and it's quite remarkable for a handwritten digit recognition task. To put that in perspective, this accuracy is right up there with some very good k-nearest neighbor classifiers for MNIST. It shows its robust ability to classify digits accurately.
Were there any digits it struggled with more?
Most digits were recognized almost perfectly. The source mentioned that only digit 9 had a slightly lower F1 score, around 0.95. This is likely due to its visual similarity to other digits, like maybe a 4 or a 7 when handwritten, but overall, extremely strong performance.
Okay, and the California housing regression, did it improve there too?
It did. The random forest regressor continued the trend of error reduction. It brought the test error down even further to $33.17 thousand.
Better than bagging's 35.35K.
Right. And the training error was also very low at $12.609 thousand. So it demonstrates consistent improvement, highlighting how random forest maintains strong performance on unseen data while keeping training error low.
Nice. Can you, look inside a trained random forest? See what it learned?
You can, to some extent. The estimators attribute gives you access to the collection of all the fitted sub-estimators, all the individual trees, so you could examine them if you really wanted to dig deep.
Okay.
But maybe even more valuable is the feature importances attribute. This provides a list, or an array, indicating how important each feature was considered to be for making the predictions, averaged across all the trees in the forest.
That sounds useful. To see which factors actually drive the house prices, for instance.
Exactly. It can offer valuable insights into your data, helping you understand which variables truly drive your target outcome. It adds a layer of interpretability, which is often very helpful.
And, as with any powerful model, I assume tuning these parameters is important.
Oh, absolutely crucial. We saw that for the random forest regressor on the California housing dataset, tuning parameters like nestimators, the number of trees, and max leaf nodes, which controls tree complexity in a different way than depth, had a huge impact.
How big?
Well, the example used randomized search CV, which is a great technique for efficiently exploring different parameter combinations without trying every single one. The best performance found was with nestimators 500 and max leaf nodes 100. That yielded an average test error of around $40.33 thousand in that specific cross-validation run.
Okay. How does that compare to bad settings?
Compare that to a maximum error observed during the search of nearly $73,000, which happened with just nestimators 5 and max leaf nodes 2.
Wow. Okay, so tuning makes a massive difference.
It really underscores that optimal performance often comes from careful configuration and iterative experimentation, not just relying on the default settings.
Yeah, these ensemble techniques really demonstrate how combining multiple, maybe individually weak or just okay models can create a remarkably strong and accurate predictive system.
It's that collective wisdom shining through. It allows us to overcome the limitations of individual learners and achieve far better generalization, moving us closer to truly reliable, real-world applications.
Okay, so that's bagging in random forests, parallel ensembles, averaging, randomness.
Now, let's shift gears to another incredibly powerful ensemble technique, boosting.
Right.
You mentioned this has a very different philosophy, sequential improvement, learning from mistakes.
That's the core idea, exactly. Instead of training models in parallel and then averaging their results, boosting trains them sequentially. Each new model in this sequence isn't just a fresh start. It's specifically built to address and correct the errors made by the previous models in the ensemble.
How does it do that?
It adaptively boosts the performance of weak learners by forcing them to focus on the examples or aspects that the ensemble previously got wrong. It's like a student who diligently reviews all their incorrect answers before the next exam, making sure they don't repeat the same mistakes.
Okay, that makes intuitive sense. What's the first boosting algorithm we should look at? Let's start with AdaBoost, which stands for adaptive boosting. It's really a foundational algorithm in this family. It laid the groundwork for many of the more advanced boosting methods we see today.
Adaptive boosting, how does it adapt?
AdaBoost works by repeatedly training a weak learner. Now, by default, for classification, this is usually a decision tree classifier with a max depth of just 1.
A depth of 1, that's tiny.
It is. We often call it a decision stump. These stumps are incredibly simple, often just making a single split on a single feature. Very weak indeed. For regression, the default is typically a decision tree regressor with max depth of 3, so still relatively simple.
Okay, so it uses these simple learners. How does it adapt or learn from mistakes?
After each of these weak learners is trained, the algorithm adjusts the weights of the training examples. Crucially, any examples that were misclassified or poorly predicted in the previous step get increased weights.
So the tough examples become more important.
Exactly. This makes those harder examples more important, gives them more focus for the next weak learner to try and get right. Each subsequent learner is essentially trying harder to fix the mistakes of its predecessors by paying more attention to the previously troublesome data points.
Okay. What are the key parameters for AdaBoost, like an AdaBoost classifier or AdaBoost regressor?
Well, there's base estimator, which is that weak learner we just mentioned, the stump or shallow tree. Then nestimator sets the maximum number of these estimators to build sequentially the number of boosting rounds. The default is often 50.
So it builds 50 stumps, each focusing on the previous one's errors.
Kind of, yeah. And then there's learning rate. This is the weight applied to each classifier or regressor's contribution to the final prediction at each boosting iteration. The default is 1.
What does the learning rate do?
A higher learning rate means individual learners contribute more aggressively to the ensemble, but there's a trade-off with nestimators. If the learning rate is too high, you might sort of jump past the best solution or even overfit. Lower rates often require more estimators, but can lead to better, more stable results. And of course, you can tune the complexity of the base estimator itself, like its max depth or min sample split, if a simple stump isn't cutting it.
Gotcha. Can you see inside AdaBoost too?
Yep. Once trained, an AdaBoost model has useful attributes like base estimator, the learner type it used, estimators, the full collection of all the fitted stumps or trees, estimator weights showing the relative importance or contribution of each estimator in the final ensemble voteridge, and estimator errors, which tracks the error rate of each estimator at its stage of training. These let you peek into the learning process.
Okay, so how did AdaBoost actually perform on our classification and regression tasks? Was it better than the single tree?
Let's see, for MNIST classification, the AdaBoost classifier obtained an F1 score of 0.712 on the training set, with a standard deviation of 0.016.
0.712. That sounds quite a bit lower than bagging or random forest's training scores.
It is, and on the test set, it yielded an accuracy of just 73%.
Only 73%? Wow. That's actually worse than the single decision tree baseline we started with, which was 88%.
It is, yeah. This is notably lower than what we saw with random forest, 97%, or even bagging, 94%. The source material specifically highlighted that AdaBoost for MNIST showed a lot of confusions that are happening between different classes.
Like confusing a 9 and a 4.
Exactly. Examples given were class 9 and 4, class 7 and 9, class 5 and 3, or class 6 and 2. This indicates it really struggled with the nuanced differences between visually similar digits, especially when using just those very simple decision stumps as its base learners.
So the stumps just weren't powerful enough to capture those subtleties.
It seems that way. The complexity of recognizing subtle curves and lines in different handwritten digits proved challenging for this sequential error-weighting approach when the base learners were so weak.
Okay, not great on MNIST. What about the California housing regression?
For the AdaBoost regressor, it made an error of $73.26 thousand on the training set, and a very similar error on the test set. The standard deviation was around 6,000 for both.
73K error. That's
Yeah.
really high. Way higher than the single tree's 37K test error, and much higher than bagging or random forest.
Unfortunately, yes. This was the worst performance among the 3 boosting regressors tested on this dataset in the source material.
Huh. Yeah.
So, while AdaBoost is a foundational boosting algorithm and historically very important to understand, its practical performance can vary greatly. It really depends on the specific dataset and the complexity of the problem. It might not always be the top performer, especially on highly complex multi-class problems like MNIST or datasets where the relationships aren't easily captured by just reweighting simple learners.
It sort of paved the way, but maybe others built on it.
Exactly. It paved the way, but others have since improved upon its core idea of sequential learning from mistakes.
Okay, so building on that concept of sequential improvement, where do we go next? Gradient boosting.
Yes, gradient boosting. This is another incredibly powerful ensemble technique that refines the idea of learning from mistakes, but in a mathematically more sophisticated way.
How so?
Gradient boosting, like AdaBoost, builds an ensemble of weak learners sequentially. Usually decision trees, but often deeper than just stumps. But here's the fundamental difference in how it corrects errors. Instead of adjusting the weights of data points,
Yeah.
each new tree in gradient boosting attempts to fit the residual.
Residuals. What are residuals?
The residuals are essentially the errors or the unexplained variance left over from the previous ensemble of trees. Think of it like the model repeatedly asking itself, okay, what did the current team of trees get wrong? Let's build a new tree specifically to predict those errors. Then, when we add this new tree's predictions to the team's predictions, our overall error should decrease.
Ah, so it's directly targeting the mistakes, trying to predict the error itself.
Precisely. It tries to optimize an arbitrary differentiable loss function, like squared error for regression, by iteratively moving in the direction that reduces the error the most. It's like walking downhill on the error surface, taking steps in the direction of the steepest descent, the gradient, hence the name gradient boosting.
And you mentioned it uses decision trees, not just stumps.
Right. While AdaBoost often defaults to very shallow stumps, gradient boosting typically uses more complex decision trees as its weak learners. Even for classification problems, it often uses regression trees internally to predict those residuals or gradients. This gives it more expressive power right from the start, allowing each new tree to potentially capture more intricate patterns than the errors left by the previous one.
Okay, that sounds more powerful. What are the key parameters for gradient boosting classifier and gradient boosting regressor?
Similar concepts to AdaBoost, but with some different defaults and nuances. Nestmators is the number of boosting stages, the number of trees to build sequentially. The default for the regressor is often 100.
So more trees than AdaBoost default.
Often, yes. And the learning rate parameter is critically important here too. It defaults to 0.1 for the regressor, which is lower than AdaBoost's default of 1.
Why lower?
This learning rate shrinks the contribution of each individual tree. It acts like a step size when minimizing that loss function. A smaller learning rate means you usually need more nestimators, to reach good performance, but it often leads to a more robust and accurate model. It prevents the model from taking huge steps and potentially overshooting the optimal solution. It encourages a more careful, gradual learning process.
Makes sense. What about the loss function?
The default loss for gradient boosting regressor is typically squared error loss, which is standard for regression. And internally, when building the trees, it often uses a criterion like Friedman-Boltz for deciding on splits, which is a variation of mean squared error designed to be more robust.
Okay, so performance. How did gradient boosting do on MNIST?
Well, interestingly, the source material explicitly leaves running the gradient boosting classifier on MNIST as an exercise for the listener.
Ah, okay. But what would we expect? Better than AdaBoost?
Oh, absolutely. Based on typical performance trends, one would expect gradient boosting to achieve an accuracy significantly higher than AdaBoost's 73%. Probably somewhere in the high 80s or low 90s percentage range, maybe even better with tuning. Its ability to learn more complex relationships by fitting residuals with deeper trees generally makes it much stronger than AdaBoost, especially on complex tasks.
Right. And on the California housing regression? Did it beat AdaBoost there?
It really showcased its strength there. The gradient boosting regressor achieved an error of $35.39 thousand on the training set with a very small standard deviation of 0.273.
Okay. Low training error. Test set.
On the test set, it made an error of $36.77 thousand with a standard deviation of 0.72.
36.77K. Okay, let's compare. AdaBoost was 73.26K, so gradient boosting essentially halved the error.
Pretty much. It's a significant improvement, showcasing its superior ability to sequentially optimize and reduce errors compared to AdaBoost on this dataset. It's also roughly comparable to the bagging result, 35.35K, and getting close to the random forest result, 33.17K.
That's impressive. Is there a downside?
Well, the trade-off is often computation time. Gradient boosting models generally take longer to run than AdaBoost, and often longer than random forests, too, because of their sequential nature and the fact that each tree depends on the previous ones. Building deeper trees also adds to the computation per tree.
Right, so better accuracy, but potentially slower training. That's a common trade-off in machine learning.
It really is a constant consideration.
Okay, so that brings us to the final boosting algorithm you mentioned, XGBoost, extreme gradient boosting.
Yes. And extreme is a pretty fitting name for it.
Why extreme?
XGBoost isn't just another minor variant. It's a highly optimized, incredibly efficient, and crucially, a regularized version of gradient boosting.
Regularize, what does that add?
Its key distinction is that it incorporates regularization terms, specifically L1 lasso and L2 ridge regularization, directly into its objective function, the thing it's trying to minimize.
Okay, how does that help?
This helps prevent overfitting. It adds a penalty for model complexity, essentially discouraging overly complex trees with large weights on their leaves. This encourages simpler, more generalizable trees, which contributes to its consistently better generalization performance compared to standard gradient boosting in many cases. Think of it like a built-in caution mechanism that prevents the model from memorizing the noise and the training data too closely.
Ah, so it's got overfitting protection built right in.
That regularization is a huge part of why XGBoost is so widely recognized and, frankly, respected in the machine learning community. It has consistently achieved state-of-the-art performance in countless Kaggle competitions and other machine learning challenges, especially on structured tabular datasets like our housing data.
Yeah, you hear about XGBoost all the time in competitions.
Absolutely. It's often the first algorithm data scientists reach for in many real-world scenarios because it hits this sweet spot offering great accuracy, often better than standard gradient boosting, but also being incredibly fast and efficient.
Why is it so fast?
It includes numerous optimizations under the hood. It's designed for parallel processing. It can build parts of trees in parallel. It handles missing values internally and quite gracefully. And it's cache-aware to work better with computer memory hierarchies. All these contribute to its extreme efficiency.
Okay. How do you use it? Is it in scikit-learn?
While AdaBoost and gradient boosting are typically found within scikit-learn's sklearn.ensemble module, XGBoost is usually imported from its own dedicated XGBoost Python library. So you'd use XGB classifier and XGregressor from there.
Does it have similar parameters?
Yes, it has a very similar set of parameters to gradient boosting, controlling things like the number of trees, nestimators, learning rate, tree depth, max depth, and importantly, those regularization parameters, regalpha for L1 or glambda for L2. It also has objective functions like reg.squaredair for regression or multi.softmax for multiclass classification. Its documentation is excellent and easily accessible.
Okay. Performance MNES-teen. I'm guessing another exercise.
You guessed it. Just like with gradient boosting, the source material indicates that training the XGB classifier on MNEST is left as an exercise. But again, in practice, XGBoost typically delivers very strong classification results. It often outperforms standard gradient boosting, potentially reaching accuracy in the mid-90s% range, or even higher on MNIST with careful tuning. Its combination of gradient boosting, regularization, and optimization makes it a formidable force.
Right. And California housing. How did it compare to gradient boosting's 36.77K error?
Here's the interesting part. The source mentioned that even with default parameters, the XGBoost regressor showed performance very similar to the gradient boosting regressor.
So around that $35,000–$36,000 error range right out of the box.
Exactly. This consistency, achieving strong results even with default settings, really speaks volumes about its robust design and built-in optimizations.
Okay, so XGBoost seems like a really strong contender, especially for tabular data.
It's definitely a go-to for many data scientists due to that remarkable balance of speed and top-tier predictive accuracy. It's a real workhorse. But remember, the source material also emphasized, again, that further hyperparameter tuning is crucial for maximizing its performance.
Right. Defaults are good, but tuning unlocks the best results.
Precisely. Experimenting with learning rate, number of estimators, tree depth, subsampling parameters, and those regularization terms can often unlock even better results and squeeze out every last bit of predictive power.
Okay, amazing. So we've covered ensembles, bagging, random forests, and boosting AdaBoost, gradient boosting, XGBoost, combining lots of models. But now, let's shift gears entirely. Let's talk about a completely different, yet equally fascinating paradigm: neural networks.
Right. Moving away from trees for a bit.
These are truly inspired by the way our own brains work, aren't they? They offer a unique and powerful approach, especially when dealing with highly complex nonlinear patterns.
That's absolutely right. Specifically, we're going to introduce multi-layer perceptrons, or MLPs. These are a fundamental type of feed-forward artificial neural network. They're characterized by having at least one hidden layer of neurons sandwiched between the input layer and the output layer.
Feed-forward meaning the information flows in one direction.
Yes. Input through hidden layers to output, no loops back like in recurrent networks. The core idea behind MLPs is that they are supervised learning algorithms designed to learn a nonlinear function approximator.
Meaning they can learn really complex relationships.
Exactly. They're exceptionally good at capturing complex nonlinear relationships within data. This makes them highly versatile for both classification and regression tasks, where simpler linear models, or even sometimes tree-based models, just wouldn't capture the full picture. They can learn highly intricate mappings from inputs to outputs.
Where do we find these in scikit-learn?
They're implemented as MLP classifier for classification problems and MLP regressor for regression tasks. They provide a robust and relatively straightforward way to build and train these brain-inspired networks within that familiar framework.
Okay, let's start with MLP classifier. For intricate classification patterns, you said.
Yes. It supports multi-class classification, like our MNEI's problem. To do this, it typically uses a softmax function for its output layer.
Softmax, what does that do?
Softmax is an activation function that's perfect for multi-class problems. It takes a vector of raw scores from the last layer of the network and converts them into a probability distribution. So for MNIST, it would output 10 probabilities, one for each digit, 0, 9, and these probabilities would all sum up to 1.
Ah, so it tells you the model's confidence for each class.
Exactly, it's very useful. An MLP classifier even supports multi-label classification, where a single sample could belong to more than one class simultaneously, maybe like tagging an image with cat, sofa, and window.
Okay, how do you actually use it? What are the steps?
The implementation steps are pretty straightforward, much like other scikit-learn models. First, you instantiate an MLP classifier object. You might pass some configuration parameters here, which we'll talk about.
Right.
Then you train it. You call the fit method with your training data, your feature matrix, xtrain, and your corresponding labels, yistrain. This is the core learning step where the network adjusts all its internal connection weights and biases through a process called backpropagation.
Okay, train it, then predict.
Yep. After it's trained, you can make predictions on new unseen data, exits. You can use predict xtest to get the actual predicted class labels, like an array saying 72151 yejuan, or you can use predict probat xtest to get those probability estimates for each class we just talked about. That gives you more nuance, showing the model's confidence, like 98% probability it's a 7, 1% it's a 9, etc.
Okay, configuration. You said that's important. What's the main thing to configure?
Arguably, the most critical part of configuring an MLP is defining its architecture, its structure, using the hidden layer sizes parameter.
How does that work?
This parameter is a tuple, a list in parentheses, that defines both the number of hidden layers and the number of neurons or units within each of those layers.
Give me an example.
Sure. If you set MLP classifier hidden layer sizes 150, that would create a network with 2 hidden layers. The first hidden layer would have 100 neurons, and the second hidden layer would have 50 neurons. The length of the tuple tells you the number of hidden layers.
Okay. How do you choose those numbers?
That's often more art than science. It's an iterative process. Too few layers or neurons, and the network might not have enough capacity to capture the complex patterns in the data, underfitting. Too many, and it risks overfitting memorizing the training data too well, and also becomes computationally very expensive to train. It can also become harder to understand, sometimes called the black box problem of neural networks, because interpreting millions of weights is difficult.
So experimentation is key there. What about preventing that overfitting?
Right, especially in these potentially very complex networks, you can use the alpha parameter. This sets the L2 penalty regularization strength, just like ridge regression. It defaults to a small value like 0.0001.
And that penalizes large weights.
Exactly. It adds a cost to the loss function for large weight values, essentially discouraging overly complex models where single connections have huge influence. It promotes simpler, hopefully more generalizable weight configurations.
Okay, what else? Activation functions.
Yes, activation functions are crucial. They sit within the neurons in the hidden layers and introduce the nonlinearity that allows MLPs to learn complex patterns. Without nonlinear activation functions, a deep network would just be equivalent to a single linear layer.
What are the common choices?
The default, and often a very popular choice in modern networks, is ReLU, which stands for Rectified Linear Unit. It's simple, fx equals x0, x. It just outputs the input if it's positive and 0 otherwise.
Why is ReLU popular?
It's computationally very efficient, and it helps mitigate a problem called the vanishing gradient problem that plagued older activation functions, making it easier to train deeper networks.
What are the older ones?
Other options include identity, which is just fxx, so no nonlinearity, rarely used in hidden layers. Logistic, the classic sigmoid function, which squashes values between 0 and 1 but can suffer from vanishing gradients. And ton, the hyperbolic tangent function, squashing values between nexa 1 and 1, also susceptible to vanishing gradients, though sometimes performs better than logistic.
Okay, so ReLU is off of the default starting point. How does the network actually learn the weights? The optimization part.
Right. The solver parameter is key here. This determines the algorithm used to optimize the weights, to find the best set of connections. Think of it like a GPS trying to find the lowest point minimum error in a very complex, high-dimensional landscape of possible weight values.
What are the options for the solver?
You can choose OutBFGs, which is an optimizer from the family of quasi-Newton methods. It can converge faster and perform better on small data sets, but it doesn't use mini batches, meaning it has to look at the entire data set at once, which can be very slow or memory intensive on large data sets.
Okay, not for huge data. What else?
Then there's SGD, which stands for stochastic gradient descent. This is the classic workhorse. It takes smaller, more frequent steps towards the minimum error, using mini batches, small random samples of the data to calculate each step. This makes it much faster and less memory hungry, especially for massive data sets, although its path towards the minimum can be a bit noisy or jumpy sometimes.
And the default.
The default, and often a favorite in practice, is ADAM. ADAM is a more sophisticated adaptive learning rate optimization algorithm. It's kind of like a smarter TPS that adjusts its step size automatically based on the terrain it's navigating. It often finds a good balance between the speed of SGD and the stability of other methods, and it frequently converges faster than plain SGD.
Okay, Adam sounds like a good default.
It often is. And for the stochastic solvers, SGD and ADAM, you can also control the batch size. This determines how many samples are processed in each mini batch before the model's weights are updated. The default is auto, which usually means min 200 in samples. Choosing the right batch size can impact both training speed and model performance.
Are there other tuning knobs?
Yes, there are others, like learning rate for controlling the step size in SGD, power, an exponent for learning rate decay in SGD, learning gradient, the initial learning rate for SPRI-D or ADAM, and shuffle, whether to shuffle samples in each training epoch for SPRI-D or ADAM. These offer further fine-tuning capabilities, allowing you to really dial in the learning process for your specific problem.
Wow, lots to configure. Can you see what it learned afterwards, like the feature importances in random forest?
It's a bit trickier with MLPs as the learning is distributed across potentially millions of weights. It's less directly interpretable than a tree or a linear model. However, you can inspect the learned parameters. The coefs attribute is a list. Each element in that list represents the weight matrix connecting two layers.
So COFES would be.
That would give you the weight matrix connecting the input layer to the first hidden layer. It shows how the input features contribute to the activation of those first hidden neurons. COVES 1 connects the first hidden layer to the second, and so on.
Okay. What about biases?
Similarly, the intercepts attribute is a list where each element represents the bias vector for a given layer, input excluded usually. Intercept 0 would be the biases for the first hidden layer. These bias values act as an offset for each neuron's activation, allowing it to fire even if all its weighted inputs are 0.
So you can look at the raw weights and biases, but it's hard to get a simple feature importance score out of it easily.
Generally, yes. There are more advanced techniques for interpreting neural networks like sensitivity analysis or LIME, but Sklern's MLP doesn't provide a simple feature importance attribute like Random Forest does. Still, inspecting coefs and intercepts gives you access to the raw, learned model.
Okay, so these parameters are powerful, letting you really sculpt the network.
Incredibly powerful. They allow you to shape the network's capacity, how complex a function it can learn, and fine-tune its learning behavior. This detailed configuration is crucial for capturing the incredibly intricate and often subtle patterns in data that MLPs are designed for, enabling them to tackle problems like image recognition, natural language processing, or complex financial modeling where other methods might struggle. They offer immense flexibility, but yeah, with that comes the responsibility of careful tuning and often more computational cost.
Right. Okay, so that's the classifier. What about the MLP regressor for continuous predictions, like our California housing data?
The MLP regressor works very similarly. It also trains using backpropagation, that core algorithm for calculating gradients and updating weights, but there are a couple of key differences tailored for regression. The main one is that it typically has no activation function in its output layer. Or you could think of it as having an identity activation. It directly outputs the continuous value predicted by the weighted sum from the last hidden layer, which is exactly what you want for regression. You don't want the output squashed between 0 and 1, for instance.
Makes sense. And the loss function?
It uses the square error as its loss function by default. This is the standard choice for regression, measuring the average of the squared differences between the model's predicted values and the actual target values. The network learns to minimize this squared error. It also supports multi-output regression, where you might be predicting several continuous values at once, like maybe predicting both a house price and its estimated time on the market.
What about the parameters? Are they different?
Here's the nice part. All the parameters for ML pregressor hidden layer sizes, activation, solver, alpha, learning gratinate, batch size, etc., are exactly the same as those for MLP classifier.
Convenient.
It really is. Once you understand how to configure the hidden layers, activation functions, and optimizers for one, you're pretty much set for mastering the other. It definitely streamlines the learning process if you're switching between classification and regression tasks using MLPs.
How do you use it then? Same steps?
Yep, the implementation steps mirror the classifier. First, you instantiate an ML progressor object, maybe setting some parameters. Then you call fit xtrain with your training features and continuous target values.
And prediction.
After training, you make predictions on new data using predictXtest. This will return the predicted continuous values, like an array of estimated house prices.
How you evaluate how well it did, not accuracy, right?
Right. Accuracy doesn't make sense for regression. Instead, you can use the score, xtest Seth White test method. For ML progressor, this returns the R2 score, also known as the coefficient of determination.
R squared. What does that tell us again?
The R2 score essentially tells you the proportion of the variance in the dependent variable, like house prices, that can be predicted from the independent variables, the features, using the model. It ranges from negative infinity up to 1. A score of 1 means a perfect fit. A score of 0 means the model predicts no better than just using the mean of the target variable. Negative scores mean the model is worse than just predicting the mean.
So the example score mentioned in the outline was around 0.45.
Yeah, 0.456788889. This indicates that about 45.7% of the variance in the California house prices in the test set was explained by the MLP model used in that specific run. Whether that's good depends heavily on the complexity of the data and the domain. It might be a decent starting point, or it might indicate that further tuning of the MLP's architecture or parameters, or perhaps trying a different model type altogether, could lead to better results.
Got it. So R2 gives you a standardized way to measure regression performance?
Exactly. It's a common and useful metric.
Okay, wow. That was quite a journey. We've taken a really deep dive into some of the most powerful machine learning models available today.
We certainly covered a lot of ground.
We started by looking at how basic decision trees, while intuitive, can easily overfit. They learn the training data too well, and then generalize poorly to unseen data. That was our baseline problem.
The overfitting challenge.
But then we saw the power of collective intelligence in action with ensemble methods. Bagging, and especially random forest, use clever tricks like bootstrap sampling of the data and introducing randomness in feature selection at each split.
Right, that randomness is key. It reduces the variance, makes the models less sensitive to the specific training data.
And the results were impressive. Random forest achieved that amazing 97% accuracy on MNIST digit recognition, really showing near human-level performance. And for regression, it dramatically cut the test error on California housing from that initial 47K down to around 33K, making predictions much more reliable.
Yeah, random forest really shown as a robust, high-performing ensemble method built on trees.
Then we explored the fascinating world of boosting techniques. AdaBoost, gradient boosting, and the mighty XGBoost. These take a different approach, learning sequentially, iteratively correcting errors.
Learning from mistakes, step by step.
AdaBoost, our first example, struggled a bit more on our complex data sets. Maybe because its default weak learners, the stumps, were too simple. Its accuracy on MNIST was surprisingly low, and its error on housing was high.
It was foundational, but maybe less effective on these specific challenging tasks compared to the others.
But then gradient boosting showed real strength. It directly fits the residuals, the errors, using typically deeper trees. It significantly improved the regression error, bringing it down from AdaBoost's 73K to around 36K on the housing data. A huge jump.
A much more powerful approach to sequential error correction.
And then XGBoost. With its highly optimized implementation, built-in regularization to fight overfitting, and parallel processing capabilities, it truly stands out.
Yeah, XGBoost often provides state-of-the-art results on structured data, which is why it's such a go-to for data scientists in competitions and real-world scenarios. It hits that sweet spot of speed and accuracy. Even its default performance on the housing data was right up there with gradient boosting.
And finally, we switched gears completely and touched upon neural networks, specifically multi-layer perceptrons, MLPs, a flexible, biologically inspired approach.
Right, learning complex, nonlinear functions for both classification and regression. They offer a powerful way to model intricate patterns in data where maybe even sophisticated tree ensembles might fall short, although they often require more data and careful tuning.
So, listeners, you now have Well, at least 3 more powerful categories of tools in your machine learning toolkit after this deep dive.
Each with its unique strengths and ideal use cases. Ensemble methods like bagging and random forest excel at transforming those weak individual learners into remarkably strong and generalized predictors. They're particularly adept at reducing overfitting and improving the stability of models like decision trees.
Boosting algorithms, like gradient boosting and XGBoost, through their iterative error correction, are highly effective at driving down errors sequentially. XGBoost, in particular, is a really strong contender for tabular data and achieving top-tier performance, thanks to its unique blend of optimization and regularization.
And neural networks, like the MLPs we discussed, offer unmatched flexibility and capacity for modeling highly complex nonlinear relationships in your data. This makes them suitable for a vast array of problems, from image recognition to complex predictive analytics, capable of learning patterns that might be invisible to other methods.
Yeah, and the key takeaway, I think, isn't just knowing what these models are. It's really understanding why they work the principles of averaging, randomness, sequential error correction, nonlinear approximation, and crucially, when to choose them based on your problem and your data.
Absolutely. And that emphasis we placed on hyperparameter tuning, especially for random forests, boosting models, and MLPs, really underscores a vital point. Unlocking optimal performance often comes from careful configuration and iterative experimentation. You need to push these algorithms to their peak potential for your specific task. Defaults are just a starting point.
Definitely. So here's a thought to leave you with. We've seen these different philosophies, parallel ensembles like random forest, sequential boosters like XGBoost, and the complex, layered approach of neural networks. As machine learning continues to evolve, how might these diverse approaches be further integrated or perhaps adaptively combined?
That's a fascinating question. Could we see hybrid models that leverage the strengths of each? Maybe ensembles of neural networks, or neural networks that incorporate boosting-like mechanisms internally, or algorithms that automatically choose and combine the best approach for different parts of a problem. The frontier isn't just about bigger data or faster hardware, but also about smarter, more integrated algorithmic intelligence.
Lots to think about there. What new insights will we uncover as we continue to push the boundaries of what these algorithms can learn from the vast oceans of data around us?
The possibilities are exciting.
Indeed. Well, thank you for joining us on this deep dive. We hope you feel a little more well-informed and maybe even a little inspired by the incredible ingenuity behind these powerful algorithms and the collective intelligence they can unlock.